Good evening everyone. Welcome to the homework portal. This is week 5. This is problem number 3. This problem will be published on the Wednesday. Okay. So this week we are having problems only on rotation. So 2 problems I hope you are already solved. So this is the third problem. A uniform rod of length 1.2 meters. Let me take this pen. Okay. I have not put on the timer. Let me put on the timer too. Right. This question is for 1 plus 2, 3 plus 2, 5, 5 plus 1, 6 plus 2, 8 plus 2, 10 marks. Okay, so I'll adjust the timer to 10 marks, 10 minutes. Let us see whether we are able to solve this within 10 minutes. Okay, done. Right, now let us continue. So therefore, a uniform rod of length 1.2 meters is at rest on a horizontal surface. Okay, this is a surface. The rod is pivoted at its center so that it is free to rotate about a vertical axis through the center. Okay, it is able to rotate like this. A particle of mass 0.2 kg moving with the speed of 12 meters per second collides and sticks to one end of the rod. So this particle, when it is incident on this part on this rod, its velocity was seen to be 12 meters per second and the mass is given here. So mass is equal to 0.2 and speed is equal to 12 meters per second. It's also given. Okay. And 6 to 1 end of the rod, the moment of the inertia of the rod is 0.18 kg per kg meter square. Moment of inertia is seen to be 0.18 and so the moment of inertia of the rod particle system is about 0.25 kg meter square. This is what is the question. So the question is so simple. So you see, initially before the particles stuck onto this one, the moment of inertia was seen to be 0.8. After the particle stuck onto this rod, what is the moment of inertia? I have not switched this on. Okay. What is the total moment of inertia? Now, total moment of inertia, I total should be equal to moment of inertia of the particle plus moment of inertia of the rod. This is what you need to do. So, how do you do this? Moment of inertia of the rod is already given here, which is 0.18. Okay. And now I will write this as 0.18 here. And then moment of inertia of the particle. So about this point, what is the moment of inertia of the particle? Where is the particle here? Particle is at this point. If I have a particle, okay, if I have a point particle which is at a distance r from a fixed point from the origin, then what is the moment of inertia of this? This should be mr square, right? Simple. So therefore, just put mr square over here. Okay, what is the value of m? Value of m is 0.2. 0.2 multiplied by what is the r? What is r here? Distance. What is distance here? If this is 1.2, this should be 0.6. This should be 0.6 square plus 0.18. When I do this, what is the answer I get? Let me take up my calculator. So this should be 0.2 star 0.36 is equal to so much plus 0.18 is equal to 0.25. 0.252 kg meter square. The answer required is 0.25. We have got the answer. Okay. So quite easier. All the questions in this are quite easier. Show that the angular speed of the system immediately after the collision is about 5.7 radians per second. Okay. Now this problem is very similar to that of, okay, so you have a particle in linear system, in linear mechanics. You had something like you had a particle of mass m which was moving with a velocity u, and there was one particle which was having a mass m2 which was at rest. Then after this collides, what will happen? So these two stick together and they start moving together, right? This is m1, this is m2, they start moving with a common velocity. Now what did you say? So you see that whatever happens in linear mechanics, the same thing can be applied for the rotational mechanics also. So here, instead of a linear velocity, you have an angular velocity. Okay. Now towards it, now what is the angular velocity of the system before collision and what is the angular velocity system after collision? This is what you need to do. So therefore here also, so instead of v, this will be written as omega. Instead of m1 and m2, this will be your total it. Okay. And then what is this one here? This will be I into omega 1. I1 into omega 1. What is the moment of inertia of this? Multiplied by the angular velocity of the particle plus what is the angular velocity of this? I2 into omega 2. Okay. So you just need to do this one here. And what is that you need to do? You need to find out the final angular velocity. So towards it, what is I1 omega 1? Let us write down this. I1 omega 1 is nothing but the moment of inertia of the particle. So what is I1 here? I1 is nothing but the moment of inertia of the particle, which should be 0.2 into 0.6 square. Let me write down 0.2 into 0.6 square multiplied by what is omega? Omega, what is omega here? The particle is moving straight over here. Okay, so the particle is not rotating. So how can you have omega here? You cannot omega have, right? Okay, but omega can also be written as V by R, right? What is R here? What is R here? R is nothing but the distance here. And what is V? 12 over here. Okay, it's given. So therefore, what I can do is, I can now write this as 0.2 into 0.6 square multiplied by 12 divided by 0.6. When I do this, 0.6 ones are 0.6 twos are, which will now be equal to 0.2 into 0.6 into 12. Let us calculate this value. So what do I get here? So I get the answer as 0.2 star 0.6 star 12. I get the answer 1.44. So 1.44 will be your L1 here. Okay, this we have got it now. So this is your 1.44 plus I2 for the rod is defined, but what about omega 2? 0, because the rod is not rotating initially, right? Plus 0 should now be equal to, this is a separate calculation, okay, is equal to, what is I total? I total just now we calculated. What is it? 0.25. 0.252 and omega. What is this omega? Omega dash, right? Which is a new angular velocity which you do not know, which you need to calculate over here, right? Which will be omega dash. So therefore, omega dash will be equal to 1.44 divided by 0.252. When I do this, what is the answer I get? So let me pull this over here. Divided by 0.252 will give you 5.71, right? 5.71 radians per second. What is expected? 5.7 over here. So this is closely 5.7. So we have got the answer correctly. Let us look at the answer once again. This is 5.714. Okay. So we are doing it correctly. Right. Now calculate the energy lost during the collision. What do you mean by energy lost? Energy lost is nothing but final energy minus initial energy. Right. Now what is the initial energy? Initial energy. Now look at this particle here. This object was at rest. So no energy for this. Right. Now what about this one? This is moving. So therefore this will have a kinetic energy. So therefore initial energy is only due to the particle, which is nothing but half mv square, which should be half into, what is the value of m? Mass of the particle. What is the mass of the particle? Is it given? Mass of the particle is 0.2 kg here, 0.2 kg here, and velocity is 12 over here. Let us take that value. So this should be half into 0.2 multiplied by 12 square, which should be 2 ones are, here goes off, 0.1 multiplied by 144, which should be equal to 14.4 joules. This is what I get. Then E final. Now what will happen to E final? When the particle is incident onto it, now this rod starts moving like this. Does it move in a horizontal way? No, it moves in a rotational manner. If it is moving in a rotational manner, then what is the energy here? The energy here is nothing but half I total multiplied by omega dash square. Now we know all the parameters here. What is that? What is half I total? I total we already found out here. How much is it? 0.252 from the first part, right? So which will be 0 half into 0.252. And what is omega t? Omega dash. What is omega dash? The final angular velocity, which is 5.71. So this is 5.71 square. When I do this, how much do I get? Let us calculate that also. So I get this as 5.71 is here, star 5.71 star 0.25 divided by 2 will be equal to 4.078. 4.078 joules energy, right? Joules over here. So what is your delta E, which is nothing but your energy loss, which should be E final minus E initial, which should be 4.078 minus 14.4. We will definitely get negative. Energy loss should always be negative, right? Minus 14.4. You should get the answers minus 10.32. Minus 10.3 joules. So thus the answer is minus 10.3 joules. Hope you got this. Okay, now let us move on to the next one. Question D. A fractional torque of magnitude 0.152 Newton meter acts on the system. What is given here? Tau is given. After it begins to rotate, calculate the angular deceleration of the rod. Okay. So therefore, what is the formula for tau and alpha? This is angular deceleration given by the letter alpha. So we know that tau is equal to I into alpha. What is tau? 0.152 is equal to, what is I here? I is nothing but the I total, the total moment of inertia of the rod plus the particle. What is that value? We already calculated this here, which is nothing but 0.252, right? 0.252 multiplied by alpha. So which implies alpha should be 0.152 divided by 0.252. How much will this be? Just a moment. Okay, how much will this be? So let us calculate this also. 0.152 divided by 0.252. So how much are you getting? 0.603. 0.6 radians per second square. Okay, we have written this also. And next, this is deceleration. So what you do is you put a negative sign here. Okay, because it is reducing, because a frictional torque is acting, right? So it means it is slowing down, right? Next, number of revolutions made by the rod until it stops rotating. See, this question also has been connected to this. Number of revolutions. Now we know before until it stops rotating. What do you mean by that? That means the angular velocity, final angular velocity is equal to 0. Then what is initial angular velocity? So initially, what was the angular velocity of the rod? That is the moment the particle hit this one, what was the initial angular velocity? That's what we need to know. So that value omega t, omega total, omega dash is 5.71. We got it here, right? So therefore, omega final or omega initial is equal to 5.71. So therefore, now you do omega final square is equal to omega initial square plus 2 alpha into theta, right? We are using the same equations what you had used in your equations of motion. So there is no change. So therefore, now you have omega final square equal to 0. Omega initial square is equal to 5.71 square plus 2 into, what's the value of alpha? Alpha is minus 0.6. Minus 0.6 multiplied by theta. Okay. So therefore, now what will happen here? So I can push this one to the other side so that this becomes positive. So you get 1.2 times theta is equal to 5.71 square, which implies theta is equal to 5.71 square divided by 1.2. How much will this be? Let us calculate that, which should be 5.71 star 5.71 divided by 1.2. How much is it? 27.17. 27.17. What is this? This is anything but your radians, the angle that we have, right? Now comes the interesting part. What is he asking? Number of revolutions. Now you know, if the rod completes one full revolution, then the angle described will be 360 degrees. In terms of radians, I should say this is your 2 pi radians. Okay. So therefore, now if the rod completes n number of revolutions, I do not know what's the value of n, that is what you need to find. So if the rod completes 2 pi n revolutions, this should be equal to this much, the total angle described, which should be 27.17. Get the value of n, which should be 27.17 divided by 2 pi. Now how do I substitute? What is the answer I get? So I will now take the calculator once again. 27.17 divided by 2 is equal to 13.58 divided by, what's the value of pi? 3.14. Okay, let me substitute that. Get the answer. You get this as 4.326, which is 4.3. Okay, so you get this as 4.3 revolutions. That means what? It describes 4 revolutions and also 0.3 revolutions. 4.3 revolutions it describes before it stops. That's what is the answer here. We already crossed the time, but anyway, it's taking more time to do it. Right. Then, in another situation, the rod rests on a horizontal frictionless surface, which means what? You have the rod like this, and it is here, and on a frictionless horizontal surface with no pivot. Oh my God, I should not put this over here. It is just standing over here. Predict without calculation the motion of the rod particle system after this collision. Now the particle comes here, it hits here. Now what will happen? As see, for example, when I have this object, okay, and it comes and hits here. Now what will happen? See, the moment it hits here, this particle starts rotating. How does it rotate? There is no pivot over here, right? It's not been fixed at one point. So, but it starts rotating about its center of mass, right? About its center of mass. So, it also starts rotating. Now, what can happen over here? Now, let us see. So, predict the motion of the rod particle system after the collision. So, what can happen over here? You can just say the first one is, you can say the particle will rotate about its center of mass. This is the first thing that can happen. This is for 2 marks. The second thing what can happen is, now as it rotates, okay, it is like you have a pen in your hand, okay, it's been shown over here, okay, so you have, let me take up something like this instead of this. Let me take up this pen over here. Let me take up this pen over here. Right. Take up a little bit slanting over here. Okay, so I cannot keep it over here. I'll take this pad and I'll keep my pen here. Okay, I'll remove this cap also. Let me say I keep my pen over here. So as a result of this, now if I apply a force over here, what can happen is the pen will move. You can try it at your place also. The pen will move. Okay, at the same time, the center of mass over here will also start moving. Okay, so center of mass will move. How will it move? Will move slightly, a little bit, parallel to the direction of the velocity of the particle. What do you mean by this? You should write this actually. Okay, so what do you mean by this? It means this will start moving. At the same time, this mass, because you are not pivoting it over here, this will also start moving like this over here. Okay, so it will be moving in the same direction here. So now the particle is here. Okay, the particle is here. So it also, so this starts a rotator. See, this is already rotated over here by a small angle. At the same time, this also would have moved by a given distance. So both the things will happen. Okay, so with this, we come to an end to this particular problem. So we already taken 6 more minutes, but anyway, I can't help because this problem is like this. So rotational dynamics will take some time for you people also to get accustomed. So come to your hand, but remember, rotational dynamics is not a tough topic. It's a quite an easy topic, and this topic, if you practice it well, then definitely nothing is difficult over here. Okay, thank you. Do subscribe to my channel for more updates. Thank you.